So here we have a problem. We're going to be dealing with something new, and I want you to just read through this and look at each of these pictures and try to choose an answer. So these are all doors. We're looking at a bird's eye view, looking down on the door where the hinges are right here. And I'm just wondering, there's these four forces. They're all 5 Newton forces. Which one is the most likely to open this door, knowing that the door is very, very, very heavy? Well, I think you can realize that when you exert your force over here, far away from the hinges of the door, that's going to make the door swing more than, pushing right here. When you try to open a door or close a door, you never push right next to the hinges. You'd have to push really, really hard if you're pushing right by the hinges to open that door. Here, when you're pushing farther away, you're definitely getting more of a capability to open the door. Over here, I don't know what this person is doing. This person doesn't know how doors work, right? You don't try to open a door by pulling on the side of the door like that. No. So what we're talking about here by this capability of getting something to swing, that's going to be something that we call torque. Okay. So torque, I like to think of it as the ability to open or close a door. That's kind of how I'm going to define torque. It's how it includes, the force that you're exerting, not just what the force you're exerting, but also where you are exerting that force, because that matters in whether or not you're going to be able to open or close your door. So when you think of torques, I really want you to try and think of opening and closing doors. So let's come back to this. Let's say this is a bird's eye view of a door, so we're looking down on the door. Here's the hinges. Let's say someone pushes, so that's going to be our pivot point. Let's say someone pushes here and someone else pushes here. As we've said, we expect that the person that pushes here is going to have a greater capability of making that door swing. So we would say that the force that's exerted out here has a greater torque. The force that's exerted closer is going to have a smaller torque. And then let's compare someone who's pushing or pulling on the door like this at an angle. Let's say both of these forces are the same. They're being exerted the same part on the door, but this person is doing a lot more in order to swing that door than this person is. And that's because this person's force is exerted directly perpendicular to the door, where this force, some of it's being wasted in just pulling. So what ends up mattering when we are calculating torque is R, where R is the distance between our pivot point and where our force is being exerted, and theta, where theta is the angle between R and F. And I think that my torque should be the biggest when these two things are at a right angle. So what function of theta is the biggest when theta is 90 degrees? Well, it's sine. So we're going to use this symbol. It's a Greek letter tau. It's kind of like a curly T, but it's called tau. Tau is going to represent torque for us. And torque is defined as, these 3 lines just mean that's how we're defining it. Torque is defined as R times F times sine of theta. R is the distance between our pivot point and our force. F is how big the force is that we're exerting. And theta is the angle between R and F. Now, for those of you who are comfortable with, multivariable calculus, you might recognize that this looks like the magnitude of a cross product, okay? And it is true that torque is a vector, technically. R is a vector because it can go from the pivot point to the point where our force is located. And F is definitely a vector. And if you take the cross product of these two vectors, the magnitude will equal R times F times sine of theta. The direction of that vector will be perpendicular to both R and F. Now, we're not really going to be dealing with this as a cross product, so I don't want you to worry too much about it. I want you to focus more on this formula here. And we're going to define a counterclockwise torque as being positive and a clockwise torque as being negative, just how we've defined counterclockwise angular velocity as positive. So in this example, when you want to know how can you tell if your torque is clockwise or counterclockwise, you just look at how the object would swing. If you exert a force on it like this object is going to swing in this direction, which is counterclockwise. So this force is exerting a positive torque. The units for torque are Newton meters. And you get that because R is measured in meters and force is measured in newtons. So we have Newton meters. That's not the same as joules. It's not the same as joules. Joules is different, okay? It just looks the same, but it's not. So torque is our rotational equivalent of force. Moment of inertia is our rotational equivalent of mass. Torque is our rotational equivalent of force. And as I said before with moment of inertia, it's not just what the mass is, but where the mass is. I'm going to say something similar with torque. It's not just what the force is, but where the force is. Because where that force is located, changes this R value, which changes the torque. And the torque is what's responsible for getting this object to rotate.